Good morning, one and all. Today we are going to discuss the closure properties of regular sets. So, what do you mean by closure property? For example, as far as integers are concerned, so suppose that I is the set of integers and the operation plus. When you add two integers, definitely you will get another integer. That means addition operation under the set integers is closed. If you subtract, addition and subtraction are also closed. Multiplication is closed, but division is not closed. Why? If 2 and 5 are two integers, these are two integers, and if you find 2 by 5, what is that? Some 0.4. That means here when you divide an integer by another integer, what will happen? The result is not an integer. That means the division operation under integers is not closed. That means if you have a set and if you do some operation, then the result also belongs to that set. That means it is closed. That is about closure. Now we are going to discuss the closure properties of regular sets. As you know, here a regular set means a regular language, and a language is said to be regular if there exists a finite automaton accepting that. And we have discussed the various tools: NFA with epsilon transition, NFA without epsilon transition, then DFA, then a regular set, various representations of regular sets. And here we are considering two languages, L1 and L2. L1 is accepting a regular set and L2 is accepting a regular set. Then what is union of L1 and L2? So initially we are taking union of L1 and L2. This L1 union L2, L1 is represented by a finite automaton, that is this one, and here you have a start state and a final state. This is the start state and this is the final state. You have, this is L2, this is accepting L1 and this is L2. That means for that also there is a start state and here you have a final state. If you take L1 union L2, that means L1 or L2, that means, or you can have another representation like L1 plus L2. L1 union L2 is, here you are going to have another final state and you have another start state. This is a new start state. Now from here to here you have an epsilon transition. Here to here you have another epsilon transition. From here you have another epsilon transition and this is another epsilon transition, and make this non-final. That means this is the finite automaton for accepting L1 union L2. That means there is a finite automaton or there is an NFA with epsilon transition accepting the same language. That means L1 union L2 is also regular. That means union operation is closed. Union operation is closed. And as far as concatenation is concerned, that means next is concatenation. As far as concatenation operation is concerned, you have, this is L1 and you have a start state and you have one final state, and for L2 also you have a start state and this is the final state. And if you take L1 union L1 dot L2 or concatenating L1 and L2, that means you are making that two a single one. That means you are going to combine those two. That means L1 followed by L2. That means here we are going to have a transition from the final state of L1 to the start state of L2. Here you have an epsilon transition and make this non-final. That means start state is the start state of L1 and final state is the final state of L2. So this is this is the finite NFA with epsilon transition which is accepting L1, L2. That means there exists an NFA which is accepting L1, L2. That means concatenation operation is also closed. What about closure? Closure. That means if you have L here, this is L. And what is L star? In our earlier discussion, we discussed how to draw. That means you are going to have an epsilon transition here. You have a start state here, and you have another final state here. Make it non-final. Have an epsilon transition, and then from here to here you have another epsilon transition. This is L star, and if you have L1, this is L1. This is this is the finite automaton which is accepting L1, and for L1 star there exists another NFA with epsilon transition. That means L1 star is also regular. Now, what about complementation? Complementation means, suppose that here you have a finite automaton, and suppose that this is the start state and this is the final state. Suppose that this is the start state and this is the final state, and suppose that this is L, this is accepting L. That means this should accept all languages which is accepted by this finite automaton. Okay, so this is a final state, and suppose that you have another final state also is there. Then after processing, that means from the start state, after suppose that your language is 0, 1, 0, 0, 1, and your sigma is say 0, 1. Your input is binary number, and suppose that your input is 0, 1, 0, 0, 1 or 1, 0. Suppose that this is a finite automaton which is accepting the set of languages which is ending with 1, 0. All languages ending with 1, 0 will be accepted. Okay. Now, if you start from here and if you process this, what will happen? If it is ending with 1, 0, control reaches any one of the final. Control will reach any one of the final states. Okay. Now, we are going to complement this. That means L bar is the set of all strings which is not ending with 1, 0. Okay, L bar is the set of binary strings which are ending with, which does not end with 1, 0. That means here L is accepting the set of languages which are ending with 1, 0. But the negation of this, that means L bar, the complementation of that is it should not accept languages which are ending with 1, 0. How will you do that? So here, starting from here, if it is ending with 1, 0, control reaches either this or this. That means if it is not ending with 1, 0, control will be in any one of the other states. So if you have to accept that language, make all these non-final and make all others final. That means rest. That means all. You have to make all final states non-final and all non-final to final states. That means that will accept the complement of that language. That means sigma star minus L means you can have sigma star means this is the closure of 0 over 1 star. This is 0 over 1 star. That means all binary strings minus L. That means L is a language and the complement of that is sigma star minus L means you have an input alphabet and you can have a number of strings or infinite number of strings that can be created or that can be the string can contain 0 or 1 or symbols from sigma, and you can have too many possible permutations of the sigma, and the language accepted is L, and if you negate or if you subtract, that means if you remove all strings which are ending with 10 in this example from sigma star, you will get the complement of that. Okay, that means complementation operation is also regular. Now what about intersection? What about intersection? L1 intersection L2. As per De Morgan's theorem, we know that L1 intersection L2 is L1 bar union L2 bar the whole bar. See, here if L1 is regular, L1 bar is regular. This is L1 bar is regular, and L2 is regular, L2 bar is also regular. And if you take regular and regular union regular, L1 bar is regular because complementation is closed under closed under complementation operation. That's why L1 bar is also regular, L2 bar is also regular. Regular union regular, that's a union operation is also closed. Again, this will be regular, and if you take the complement, that also will be regular. So intersection operation is also regular. Then what about difference? Difference is L1 minus L2. L1 minus L2 you can have in a different way. You can represent that in a different way. L1 intersection L2 bar. L1 minus L2 in L1, not in L2. That is mean. That means if you take the intersection of that L1 intersection L2 bar, this is the representation. And see, suppose that this is L1 and this is L2. This is L1 and this is L2. L1 minus L2 will be this portion. Okay. So L1 intersection L2. What is L2 bar? L2 bar is this portion. This portion. So if you take L1 intersection L2 bar, you get this portion. Okay. That means L1 intersection L2 bar. Here L1 is regular, L2 is regular. As L2 is regular, L2 complement is also regular. Then if you take the intersection, we have already proved that intersection operation is regular. That's why difference is also regular. Now we are going to discuss a reversal operation. String reversal operation. For example, if you have a language L, then L raised to R, which represents the reversal of string. That means, reversal means if L is accepting ABC, a string ABC, then L raised to R will accept CBA. That means in L, you have L is accepting a set of languages and L raised to R is accepting the reversal. For example, if it is accepting 1010, then L raised to R is accepting 0101. Okay, that means if you have a string, then the reversal of that language means whatever language L is accepted, then L raised to R is accepting the reversal of that. That means every string has to be reversed. That is accepted. And here we are going to have, suppose that this is a finite automaton which is accepting, here you have a start state and this is accepting the language L. Suppose that you have more than one final state, and if a valid string is accepted from the start state, it is reaching any one of these final states, any one of the final states. So if it has to accept the reversal of this, if it has to accept the reversal, that means if it has to accept L raised to R, what will happen? You have to have a new state here, and now you have to make, see, you have to make every final state a start state. These are all start states. Every final state has to be converted to start states. Now this is start state, this is a start state, and this is a start state. And make the start state a final state. That means convert final states to start states. That is 1. And 2, convert start state to final state. Convert start state to final state. And now what you have to do is, you have to, here if you have more than one final states, here for this, in this example you have more than one final state. If you have only a single final state, then after this reversal you have only a single start state. In that case there is no need to have any modification. But if you have more than one final states for R, then when you are converting these final state to start states, what will happen? You will have more than one start states, but that is not allowed. If you have more than one start states for L raised to R, what you have to do is create another start state here. Then you have to give epsilon transition. You have to create epsilon transition to the new start states and make all of them non-final. Okay. So for the original L, we have only a single start state, and suppose that we have more than one final states. What you have to do is convert all final state to start states. Okay. So if you have more than one final states for the original L, then after this conversion you will have more than one start states. But definitely there is a single start state for our original L, and when you are converting that, this is the final state. Okay. Now if you have more than one start states for the revised, or for L raised to R, revised finite automaton, what you have to do is, you have to create another node and make it as the start state of L raised to R. Make it as the start state of this, and have epsilon transitions to the new start states. Okay. Then after that, what you have to do is, in the original L, if you have, say, from P to Q, suppose that you have states, you have two states P and Q in this, and if you have a transition P to Q, then you have to reverse that. Now you have to set it as Q to P. That means every arrow has to be reversed. That means if there is a transition from P to Q, you have to change it to Q to P. If you have self loops, there is no change. That means there is no need to alter self loop. That means if you have, say, from this is the self loop, no need to change it. These are, that means 3, reverse the direction of all transitions except self loops. Okay. So when you do this L raised to R will accept all strings which are in reversed form. That is reversal. Now we are going to discuss homomorphism. The next one is homomorphism. Homomorphism is called otherwise substitution. Another name for, in mathematical terms, substitution is called homomorphism. Homomorphism is h of L is equal to h of W, where W is an element of L. I'll show you an example where this H is a mapping from sigma to tau star. For example, suppose that sigma is equal to say 0, 1 and say tau is equal to say A, B. That means here you have two sets of alphabets. Here sigma is 0, 1 and tau is AB. That means H is a mapping from sigma to tau star means we are going to substitute each 0 with the function is, suppose that the function is like this, H of 0 is equal to say AA and H of 1 is equal to say BB. See here H of 0 is equal to AA and H of 1 is equal to BB. That means this homomorphism, that means you are going to substitute AA for 0 and BB for 1. BB for 1. That is the meaning. That means H of L means you are in this language you are going to have a substitution. Substitution means that substitution, that mapping, H is a mapping from sigma to tau star means for every symbol of this sigma you are going to have a string from tau. That means that is another alphabet. That means you are going to substitute AA for 0 and you are substitute BB for 1. That is the meaning. That is substitution. And now suppose that you have say 0 or 1 0 followed by 0 1 star. Suppose that you have such a language. That means 0 or 1 0 star 1 0 1. That means this is the language accepted is L. And what is H of L? That means you are going to substitute AA for 0 and BB for 1. That means L is equal to 0 or 1 0 star 0 1 is regular. Why? That is represented by a regular expression and definitely this is representing a finite automaton. That means this is a valid language and once you substitute AA for 0 and BB for 1, again that also will be regular. That means H of L is equal to, you are going to substitute AA for 0, BB for 1, again 0, AA star, followed by what is 0? AA and 1 is BB. That means AA or BP, AA star, AA, BB. This also is regular. Why? This is a regular expression. Since you have a regular expression that can be easily accepted by a finite automaton. That means homomorphism is also regular. Okay. Now we are going to discuss inverse homomorphism. Inverse homomorphism is the reverse of homomorphism. That means homomorphism you are going to substitute, and after substitution you are trying to retrieve the original expression or original string. Suppose that H of 0 is equal to A, that means this is the homomorphism. That means you are going to substitute A for 0. H of 1 is equal to B means you are going to substitute B for 1 and H of 2 is equal to AB means you are going to substitute AB for 2. And in reverse time, H inverse of A is equal to 0. That means A is substituted for 0. Then when we are reversing the operation, H inverse of A is equal to 0, H inverse of B is equal to 1 and H inverse of AB is equal to 2. Now sigma, the input alphabet, is containing 0, 1 and 2, and tau another input alphabet, which is, that means this is the original expression and here we are going to convert, or here this is the substitute alphabet. This is going to be substituted for sigma. That means homomorphism. And suppose that you got a language L which is AB. What is H inverse of L? See, H inverse of L means here A is actually substituted for H is A is substituted for 0, that means 0. Then B is substituted for 1. Again A is substituted for 0 and B is substituted for 1. This is one possibility. Now say AB. Now A is substituted for 0, B is substituted for 1. Then instead of taking A and B as separate entities, you have to take AB as a whole when AB is substituted for 2. This is another possibility. That means when you are reversing this is another possibility. And next one is AB. That means here take this as an entity. Then H inverse of AB is 2 and A is 0 and B is 1. Then take this as AB and this as AB. Okay. Then this is 2. These are different possibilities. But when you are reversing that, this is called inverse homomorphism. That means you have a string, and after substitution you got the string. Then if you, this is the substituted expression, and from this we are trying to retrieve the original one, and there are different possibilities, that is 0 1 0 1 0 1 2 2 0 1 and 2 2. Okay, that means here we have another expression, that means H inverse of L is equal to L. H of H inverse of L is equal to L. That means when you are substituting this, suppose that you have an expression, say AA plus BB. This is not AA plus BB. H inverse of L. Suppose that represents A or AB star B. What will happen? Suppose that H inverse of L is this. Then what will be the original L? L is equal to A is substituted for 1 or 0 and AB is substituted for 2. That means 0 or 2 star, what is B? 1. This is one of the possibilities. That means when you are reversing this, that is one of the possibilities. Anyway, this is the inverse homomorphism operation, and if you have a language accepting the substituted expression, then definitely the original expression also is representing another regular set. That is the point of discussion, point of conclusion here. Now we are going to discuss the last one, which is the quotient operation. When you have two languages L1 and L2, what is the quotient? You have two types of quotients, left quotient and right quotient, and actually you are cutting either prefix or suffix. That means left quotient means it is cutting the prefix. When you do an example, it's easy to understand it. And left quotient means you are cutting the prefix, and right quotient is you are cutting the suffix. L1 by L2 is equal to x such that xy is an element of L1. That means if xy belongs to, if L1 is equal to xy and L2 is equal to say y, then L1 by L2 is equal to x, L1 by L2 is equal to x. That means you are cutting the suffix. This is right quotient, cutting the suffix. And if xy is this and if it is x, then L1 by L2 is, if you are cutting the prefix x and L1 by L2 is equal to y, that means there are two types of taking the quotients. That means you are cutting either the suffix or the prefix. If you are cutting the prefix, it is called left quotient. And if you are cutting the suffix, then that will be right quotient. Okay, that is the definition of this. When you are doing an example, this is an example, and L1 is 1 0 1 0 0 1 0 1 0 1 0 1 1 1 0, and L2 is this one, and L1 by L2 is this. And if it is left quotient is cutting the prefix. That means cut prefix. We are cutting the prefix. Cutting the prefix means, say 10 by 10, you are going to verify whether the left end is 10. That means 10 and 10 are going to cut it, and now you have epsilon. What remains is epsilon. And when 100 and 10, you are going to verify whether 10 is a prefix of this. That means you have a prefix 10, you are going to cut it, and whatever remains is 0. And for this 10 by 10, again you are going to verify whether 10 is there initially as prefix. Here we have a prefix 10, and after that you have another 10 remains, and here also you have 10 as the prefix. What remains is 1110. 1110. Okay, so this is the left quotient. And what is the right quotient? Right quotient or cut suffix. Cut suffix is this is 10 by 10. This is the suffix as well as the prefix. When you do that operation, again epsilon. But here 100 and here it is 10. We don't have any 10 on the right as suffix. Then it is again the quotient is epsilon. 10 by 10. Here 10 is there as a suffix. Then you have to cut it, and what remains is 10. And here also you have a suffix 10. What remains is 1011. This is 1011. Okay, that means this is the left quotient and this is the right quotient. This is actually, in a language you have something, and after the quotient operation you are cutting either the suffix or the prefix. So if you are cutting some, what remains is again a regular set. That means after cutting either the suffix or prefix, definitely there exists a finite automaton for that. Definitely a finite automaton exists after cutting the suffix or prefix. That is why this quotient is also regular. That means here we have considered union, concatenation, closure, complementation, intersection, difference, reversal, homomorphism, inverse homomorphism, and quotient. All these operations are closed and closed for regular sets. Okay, so in this class we have discussed the closure properties of regular sets, and this is very important as far as our examination is concerned. So you have to go through all these operations, and the proof of this is not required. You understand that all these operations are closed for regular sets.